Welcome. We will introduce the concept of infinite series and sequences in this video. And as you're probably already familiar with my style, whenever there's a tie-in with something to scripture, I like to make a little side note. And so before we get into the topic, I'm going to just give you a little flavor of something spiritual, and this ties in with the attributes of God. Here's a premise. God may never be fully comprehended since he is infinite, okay, so this is the tie-in for today's lesson, whereas his creatures, namely us, are finite. And so oftentimes you may hear someone they may interject and say, well, this doesn't make sense. Of course, many things may not make sense because God is infinite and we are not. If everything made sense about who God is, then in a sense, God wouldn't be God after all, now would he? Because we're saying by our opening premise that he is very, very different from us in that he's infinite. Well, he is singular. I won't go through all of the attributes, but he is singular. In Isaiah 40:25, he says, "To whom will you compare me, or who is my equal?" Isaiah 46:9 says, "I am God, and there is no other. I am God, and there is none like me." But coming to the fact that he is infinite, let's just take a look at a few things about this. When Moses was in communication with the Lord, and he said, well, Lord, who shall I say sent me? And God said, I am who I am. This is the YHWH, or Yahweh, attribution. That means his existence is eternal, it's indefinite, it is not changing. In Psalm 147:5, the psalmist writes, "Great is our Lord and mighty in power, his understanding has no limit." Okay, so we're going to talk a little bit about these concepts in the mathematics. Having no limit means that God is infinite. And another attribution is El Olam, the everlasting God. Isaiah 40:28, the Lord is the everlasting God, and his understanding no one can fathom. Yes, that's exactly what we were just saying a moment ago. Isaiah 55, verses 8 and 9, "For my thoughts are not your thoughts, neither are your ways my ways, declares the Lord. As the heavens are higher than the earth, so are my ways higher than your thoughts." 1 Corinthians 2:16, "For who has known the mind of the Lord, that he may instruct him?" Revelation 1:18, 21:6, 22:13, all basically say, when God is saying, "I am the Alpha and the Omega, says the Lord God, who is, and who was, and who is to come, the Almighty." So he's the beginning, he's the end. I like what Clement of Alexandria had said, a 2nd century philosopher, "The Alpha and the Omega, of whom alone the end becomes the beginning, and ends again at the original beginning without any break." That is to say, there is a circularity of God's existence in that his beginning is the end, and vice versa, such that he has no beginning and he has no end. Okay. So that is my little side note for us as we delve into this subject of infinite series and sequences. So let's start off with something very simple and basic. Let's compare a couple of fractions. So I have 1/2, and then next to 1/2 we have the fraction 1/9. We can write these in decimal form. 1/2 would be 0.50. But notice that 1/9, if you were to try and write it in decimal form, you would have to write 0.1, and then you'd have 1, 1, 1, and these ones would go ad infinitum. That is to say, the ones are repeated interminably. And so that's why I've noted the 1 with this overbar. That overbar indicates that the 1 is repeated over and over and over again without end. So if we were to wonder how can we get to this, we might take a quick stab at it by saying 1/10 is a pretty close approximation to 0.11111. 1/10 is just 0.1, but it's not as accurate as we could make it. So to get a little more accurate, we could add to 1/10, we could add 1/100th. Okay, so 1/10 is 0.1, and 1/100th is 0.01. And so if you add these two, you're going to get something a little bit closer to what we're looking for. You get 0.11. If you continue this process ad infinitum, look at what you have. You have 1/10. Okay, so this is the 0.1. This is the 1/100th. This is the 0.01. And then this is the 1/1000th. This is 0.001. And if you just keep doing this in ad infinitum, in the limit, as that process goes to infinity, you will get identically the fraction 1/9, which is what we were seeking to get from the beginning. Now, the terms on the right-hand side, these terms, the 1/10 and the 1/10, 1/10 squared and 1/10 cubed, so forth, these can be put in terms of a sequence. So let's define what a sequence is, because this is something that comes up again and again. A sequence, let me first give a loose understanding of what a sequence is. So loosely, a sequence is an ordered list It's an ordered list of objects. Okay. In this particular example, it would be the 1/10 to the first power, comma 1/10 squared, comma 1/10 cubed, and comma ... meaning it goes on forever. Let's make it a little bit more formal. So a sequence, in fact, is like a function. So I could say like a function, say f, which has as its domain the set of natural numbers. Sometimes we will abbreviate natural numbers in this way. We'll put this fancy looking n, and all that means is the set of the counting numbers, which are 1, 2, 3, ... So those go on for ad infinitum. So, and if that's its domain, look at its range. Its range is going to be f evaluated at 1, f evaluated at 2, f evaluated at 3, ... Okay, so we see a mapping that takes place between these two sets, such that I could say, therefore, f is a map that takes something from the natural numbers set, which is the 1, 2, 3, so forth, and it puts it into its range is something real in this context, okay? Or if I would replace f, this little f, instead of writing f, because when we talk about sequences, usually we're not using the symbol f like you would in the normal sense of a function. Normally we would rather write it as a sub n is the map taking things in the domain of the natural counting set into the infinite real numbers. Of course, both of these sets are infinite. Their sizes are, however, different. Their cardinalities, let me say it that way. Where the way I've defined a sub n, I hope you appreciate that it is the same as f of n for all n. Okay? Now, Therefore, the sequence that we were talking about here can be written this way, okay, where we note here the nth term. So this is the first term, this is the second term in the sequence, the third term in that listing, and this is the nth term. In this notation, we can say that the general nth term, which we will abbreviate as a sub n, is this, okay, or I could say it even more compactly in this fashion. Okay, so I pick out the nth term, and I say that the set of all the an's is 1 over 10 to the nth power, where, of course, n is coming out of the set 1, 2, 3, ... Okay, so let's keep going here. So the sum, this sum, 1 over 10 to the first power 1 plus 1 over 10 squared plus 1 over 10 cubed plus ... This is an infinite series. An infinite series very simply can be thought of as a sum. So whenever I say series, think about sum. When we talk about sequences, we distinguish that from the series in that a sequence is more of an ordered listing. Okay? So I could say the first term is a sub 1, which is this guy, plus, okay, so it's a sum, right? It's a sum, so I have a plus here. The second a sub 2 is that term, and so forth. Now, you've probably seen this before, but we can also denote sums with this Riemann sum notation. Using a Riemann summation, that's just the capital Greek letter sigma, and we note our index runs from little n, is starting at 1 and goes ad infinitum, so this symbol is infinity. So for our example, we could say that 1/9 is equal to the sum, as n runs from 1 to infinity, of 1 over 10 to the nth power, where, of course, if we were to write this out, we would say that the first term is 1 over 10 to the first power, plus, that's what this symbol means, plus 1 over 10 squared, plus 1 over 10 cubed, plus ... and that runs on ad infinitum. Now we come to another concept. The concept that I'm referring to is the finite. This is not infinite, but it's finite. The finite nth partial sum of a series we can write in the following way. I can say, oh, by the way, before I move there, let me come back here for 1 second. So the sum, as n goes from 1 to infinity of the an, can also be written in this fashion. It's the limit, as n goes to infinity, of the nth partial sum s sub n. So I skipped over a couple things here. Let me backtrack just momentarily. If I were to write this out, I could write this in terms of the finite nth partial sum as the following. I could say that we have s sub n is equal to a1 plus a2 plus a3 plus ... plus an, and it's finite because I'm terminating this sum at the nth level. Okay, so I could say therefore that the sum going from 1 to infinity of an is the same thing as the limit as n goes to infinity of the nth partial sum. Okay? Let me write this out in a little more formal fashion here. So I could say that an infinite series can be written as the summation of a n's as n runs from 1 to infinity is equal to the limit as n goes to infinity of s sub n. Okay, and if that sum actually exists, we can call that S for the sum of that. So if sum exists, we can denote it as that S over there. Now, let me say this a little more formally. Provided that the sequence of partial sums, we will abbreviate the sequence of partial sums with this brace, in these braces enclosing this S sub n, converges to a finite limit S, then this converges to that sum S. Okay, and we write exactly what I wrote here. Okay, that is to say that as n goes from 1 to infinity of a sub n, we get this to equal the cap S. If the sequence of partial sums does not converge, then the original series, which is this, is said to diverge. Okay, so far we've introduced 4 basic concepts. Let me summarize the 4 basic concepts that we've discussed so far. So there are 4 ideas discussed so far. Here they are. Number 1, a sequence. This is an ordered list. Number 2, a sub n, which is the nth term in a sequence. Sometimes it's also referred to as the general term. 3, an infinite series. Okay, what did we say an infinite series is? Series is a fancy word for an infinite sum. So anytime we say series, think about the word sum. And then the last idea that we just introduced right now is this capital S sub n, which is the nth partial sum of the infinite series. Okay, very good. So before I move on, let me just remind us that this a sub n, you can think of it as a function. The way that it differs from a function is that when you map this out, you're mapping at those discrete locations, meaning normally a function is thought of as being continuous. So let's suppose you have a function that does this, whereas in our case you would have something that may do something like this. So each of these points that I've drawn correspond to these integral values 1, 2, 3, but you don't connect these with a straight line because remember that our map goes from the natural numbers, and so there's nothing to draw from in between these integers, okay? So that's how the a sub n is a little more, it's discrete in that sense, whereas this is more of a continuous function. Okay, that's how they differ. Alright, that's an important detail, but maybe not so important for what we're trying to do at this exact moment. Now we go on and we introduce probably the most fundamental of all the series that you would encounter, and that is the geometric series. Okay, a geometric series has the following form. It has the form that you have the sum ranging from 1 to infinity, of course, of AR to the n minus 1. So if I were to expand this out, I get, when n is 1, I find that 1 minus 1 is, I get an AR to the 1 minus 1 plus, okay, that's what this summation symbol means. When n is now 2, you get AR 2 minus 1 at the exponent, plus when n is 3, you get AR cubed minus 1, plus, and of course this continues, you go to the nth term, it becomes AR to the n minus 1, this is when n is equal to n, and of course this continues ad infinitum. Okay, so let's look at each of these. This 1 minus 1 is 0. So r to the 0 is just 1, so you get an a. Okay, so you get AR to the 0, but AR to the 0 is just 1. So you really get an a there, plus you get AR to the 1 plus AR squared plus dot 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 plus AR to the n minus 1 plus dot dot dot, which is a plus AR plus AR squared plus dot 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 AR to the n minus 1 plus dot dot dot. Okay, let's define what these things mean. This first symbol, A, is known as your first term. Obviously, A has to be different than 0, because if A were 0, that means that we're not even talking about a geometric series. The geometric series has of the form A times something. Well, if A is 0, you don't even get this form, because it just wipes everything else out. So obviously the first term must be different than 0. That's an important thing to note. And the other thing we see here is this symbol R, which stands for the common ratio. Now it turns out that in a geometric series like we have here, you can always find what the common ratio is by dividing. So to find what R is, divide any term by its predecessing term. So for example, let's just take this term. So here's a little small example. I'm taking when n is equal to 3, we get AR squared. and the predecessing term is this term, so I divide by it, I get AR. Notice that the A's cancel, okay, and I'm left with R squared over R, which is just R. Okay, so anytime you need to find what the common ratio is in a geometric series, the simplest thing to do is just pick a term and divide by the term that came before it, and you'll get your common ratio R. Here I have to make a few notes, so let me note, first of all, note 1, that if R is 1, look at what happens. If R happens to be 1, you get that S sub n, this is the nth partial sum, is equal to A, I'm just reading from here, plus you get A times 1 plus A times 1 squared plus dot 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 plus A times 1 to the n minus 1 plus dot dot dot. But all of these are just 1. This is 1. That's just 1. That's just 1. This is just 1. So really you have A plus A plus A plus dot 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 plus A plus dot dot dot. And you have n of these things. If you were just talking about there should not be a plus dot 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 here. We're talking about the nth partial sum. This is finite. Okay, I apologize for that. So you have n of these, and so notice that this means that S sub n is equal to, you have n of these, so I could write this very simply as S sub n, the finite nth partial sum, is just n times A, whatever n may be. It could be 10, it could be 100, it could be 1,000,000. It's always, whatever number it is, it's always going to be a finite quantity or a sum. So that, look at what we can say here, so that as n gets to grow without bound, that means as n tends to infinity, then you have these things to note. For A positive, your nth partial sum is going to be tending towards plus infinity, and for A negative, your nth partial sum is tending to minus infinity. And so in either case, the sequence of your n partial sums diverges. Okay? As does the geometric series. Let me abbreviate geometric series as GS. Okay? That is a very important note. That is when R was 1. Let's note another thing here. Note number 2. How about if R is different from 1? If R is different from 1, we can write S sub n in a closed form manner by subtraction. Let's look and see how to do that. So here is how we can do that. I could say that S sub n minus R times S sub n. Look at how I subtracted that. That is to say, A plus AR plus AR squared plus dot 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 plus AR to the n minus 1. That's this first part. Minus, now I'm multiplying S sub n times R, so I get minus AR plus AR squared plus AR cube plus dot 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 plus AR to the n. Okay? Well, notice that this term here is wiped out by the minus of that term there. this term here is wiped out by the minus of that term there when you distribute this minus in. Okay? So all of these terms get wiped out. The only surviving terms are the first term survives, and of course the last term survives. So look at what we have here. We get that, therefore, Sn minus r times Sn is equal to, the first term is this, and then you get minus a times r to the nth power. This is that term which also survives. And so we get that if I factor out an S sub n, I get that S sub n is equal to 1 minus r is equal to, I'll factor out an a here, a times the quantity 1 minus r to the nth power. And so I find that S sub n is equal to a times 1 minus r to the n over 1 minus r. Of course, this is only going to work if r is different from 1. Okay, that's what we were saying over here. Obviously, if r is 1, then it's not going to make any sense because you're dividing by 0, which is undefined. Okay? Here is another note. Note number 3. How about when we look at the absolute value of r being less than 1? Okay, so these are all numbers like, for example, 0.1, 0.2, minus 0.5, minus 0.9. All of those fall in this category. So if the absolute value of r is less than 1, then as n goes to infinity in this expression over here, notice that the r to the nth power is going to go to 0. And you may say, why would that happen? Because if the absolute value of r is less than 1, let's say it's, I'm just going to make a number up, let's say it's 0.1, then as the exponent here is getting really, really big, let's say it's 2 to begin with, then it grows to maybe 20, then it grew to 200, and then it grew to maybe 5 million. Well, when you take such a large exponent on such a small number, bounded between 1 and minus 1, which is what this is saying, not including those endpoints, this term is going to go to 0. It's going to vanish. And because of that, I can write this expression in the following way. Therefore, the limit as n tends to infinity of S sub n is going to be a 1 minus, of course this went to 0 now, over 1 minus r, and this is the sum which we were denoting as capital S before. Okay? So that is to say, this is a very important point, that the sum of a geometric series is equal to a over 1 minus r, provided that the absolute value of r is less than 1. Okay, a very important point over here. So this is a convergent limit of a geometric series when the absolute value of that common ratio is less than 1. All right. Excuse me. let's just look at a couple other points here. Supposing that r is strictly greater than 1. Then, as n grows without bound, this term, r to the nth power, which is up here, of course, which is the one that we circled up here, that's going to tend to infinity, since r is strictly larger than 1. And so the sequence of our n partial sums diverges, and so does our original geometric series. Look at what happens when r is strictly less than -1. So it might be -2 or -10 or -100. Then the r to the nth term actually oscillates from negative to positive in bigger and bigger absolute value terms, depending on whether or not n is odd or even. And so once again, our sequence of partial sums diverges. If r is exactly -1, then our sequence of partial sums becomes a in the first case, when this is when, of course, n is 1, okay? And if r is -1, then a minus times a minus up here becomes a plus, so you get a +2, and then you get a +2 back down here, so the 2 over 2 cancel to 1, you get an a. But in the next case, when n is equal to 2, you get a square here, so you get this 1 minus a 1 goes to 0, so this then becomes 0, and it just toggles between a and 0 ad infinitum. And because it's not settling to any one particular value, and we also know by definition that a is not ever going to be 0 by definition, that means that it's going to diverge. So all this to say, the one most important point, let's summarize it, that the only time the geometric series converges is when the common ratio in terms of absolute values is less than 1. Okay? That's the only time it's going to converge. Anything other than that, it's going to diverge. A very important point. Now, let us look at some little examples here, so we could get a little practice at what we're talking about here. The first example says, let's find the 10th partial sum of this series. Okay, so we have 4 plus 8 plus 16 plus 32. You'll notice that there's a pattern here. The succeeding term is always double its predecessor. So 8 is double that of 4, 16 is double that of 8, and so forth. So here we note that if we note that by dividing all terms after the first by the preceding term, we get our common ratio. Our common ratio is, as we just said, since everything is getting doubled, our common ratio is r is 2. Okay? We can see that by doing 16 divided by 8, or 32 divided by 16. And that means that our ratio there, the common ratio, is 2. Okay, this series here happens to be a geometric series. Of the form a plus ar plus ar squared plus ... A is our first term. Okay, that's this guy right here, our first term. So that means we have 4 plus 4 times 2 plus 4 times 2 squared plus ... So we use the result we just found. Therefore, our nth partial sum is a times 1 minus r to the n over 1 minus r. That means if we're interested in the 10th partial sum, I can denote that as s sub 10. That means I get 4 for a times 1 minus r is 2. N here is 10 over 1 minus r is 2. And if you do that on your calculator, you should be able to show that s sub 10 is this pretty large number, 4,092. Okay? Let's look at another example. We know that 0.33 with the overbar, that means that goes indefinitely, is the sum, the infinite sum, 3/10 plus 3 over 10 squared plus 3 over 10 cubed plus dot dot dot. Here, a, the first term is 3/10, the common ratio is 1/10, and here, since the absolute value of r is less than 1, okay, because why is that? Because the absolute value of r is just 0.1. So 0.1 is indeed, the absolute value of 0.1 is still 0.1, is indeed less than 1. So we know that our infinite series here is going to converge to the sum s, such that in the limit as n tends to infinity on the nth partial sum, we get this formula which we saw before, and if I plug everything in, I get 3/10 is over 1 minus 1/10 is r. That gives me the 1/3. Okay, I'm not going to do this just for the sake of time, but here's something for you to try out. Can you write this decimal in terms of a fraction of integers, m over n, where n is different from 0? Can you try your hand at that? I won't do it, but I'll maybe give you a little head start. Okay, I'll say that this is equal to 0.1 plus 0.216794, 216794, and this pattern of 216794 keeps on repeating itself. So you could see that the second term is geometric, meaning this term is geometric. So I'll give you that much of a head start or a hint, and you can see also that a, the first term in this geometric series is 0.216794, and then you get an r. You can verify this is 1/millionth. Okay, we can write 1/millionth in scientific notation as 10 to the minus 6th power. Of course, obviously, the absolute value of r here is much, much less than 1. Okay, so we expect there to be a sum. So you can go ahead and find your sum in this form. And I'll just give you the answer. You show on your own that if you were to write this out, you can write this as this number. It's 3,167,939 divided by 9,999,990. Okay, I won't show those remaining steps, but I think you got the drift and you can do it on your own. I'm going to do this example and then I'll come back to our final example for this video. Here we want to write this fraction, write the following as an infinite series in powers of x. And we also want to find the domain of validity. Okay? So, well, we already know the result of a geometric series. We've already shown that. It's a over the expression 1 minus r. So I want to conform. So as for a solution, we want to conform this into this form. So I've got a 1 sitting down here in the corner, but I've got a 3 sitting over here. So what I could do is I can divide top and bottom of this. Dividing top and bottom by 3, I'm going to get 6 divided by 3 over 3 divided by 3 plus the x divided by 3. That's going to give me 6 divided by 3 is 2, 3 divided by 3 is 1, plus x over 3. Now this and this are comparable, right? They're in a similar format. So by inspection, we see that the a, which is this term here, is really 2 in our case. That's this term. Okay, and our r, the common ratio, which is this term here, is this term in our case here. It's x over 3. Oh, I'm sorry. I have to say it's minus x over 3, right? Because we have a minus here and I have a plus here, so it's really minus x over 3. Okay, so the domain of validity is, well, we know that it's going to happen when the absolute value of our r is less than 1, strictly less than 1. That means, in our case here, that means minus x over 3 in absolute value terms is strictly less than 1. And what this means is that you have x over 3, if I take it out of the absolute value terms, it's going to be between minus 1 and 1, strictly between minus 1 and 1. Now if I multiply throughout by 3, I'm going to get that this is minus 3. X is between minus 3 and 3, strictly between minus 3 and 3. So the domain of validity, that is to say where it's going to converge, is the absolute value of x must be less than 3, or that x is strictly between minus 3 and 3. Okay, so by the way, we can write this out a little bit. We can say that therefore 6 over 3 plus x I could write in an infinite series fashion as follows. Here's my first term, a is 2, plus 2, that's the a again, times the r, which is minus x over 3, plus the 2, which is the a once again, times the minus x over 3 squared, plus dot dot dot. So I could write 6 over 3 plus x in an infinite series term. I can pull out the common 2, which is the first term, and then I'll get 1 minus x over 3 plus x squared over 9, which is that term right there, and then it just continues, minus dot dot dot. So it goes plus minus, and it goes like that forever ad infinitum. Okay? Our final example I'm going to go back up a page here, is this one. And it's a famous or a classic, you might call it the classic bouncing ball problem. And here we have a ball that is dropped from a height of 50 meters. Okay, so the height up here is 50 meters. And on each successive bounce, it rises only to 3/4 the height that it was in its previous height. So it starts at 50 meters, then it hits the ground, then it bounces up, but it's only going to rise or rebound to 3/4 of that value. So height number 2, we can say, is equal to what it was originally, 50 times 3/4. And if you do that on your calculator, you'll see that it's 37.5. And then height number 3 is going to be 50 times 3/4 squared. Okay, so it's excuse me, it's the first height, it's the second height, 50 times 3/4 times 3/4 of that. So if you were to do that, you're going to get 28.125 meters. And then height number 4 is going to be the predecessing one times another 3/4, so it'll be 50 times 3/4 cubed. And if you were to compute that on your calculator, it's going to be this number, 21.09375, and etc. Okay, and this is going to keep on going like that. Now, to solve a problem like this, it is a good idea. We see that there's a pattern, and we can make this pattern completely symmetric if I add in a fictitious, this fictitious rebound. So let's add in fictitious rebound of 50 meters at start. Okay, prior to actual 50-meter drop. Okay, so it's actually starting here and dropping, but we're pretending that it's rebounding up before it's dropping down, and then we'll correct for that later on. So to do this, then, the total distance that the ball travels as it bounces up and down, up and down, up and down, let me call that D. That total distance is going to be 50 times 2, that's this 50, and also this 50. So that's why I have 50 times 2 plus I get 50 times 3/4 to the first power, which is this height 2, times 2 of them, because I have the one that rebounds and then the one that drops, plus 50 times 3/4 squared times 2 plus ... and that goes on ad infinitum. But since I added in this fictitious rebound of 50, I'm going to then just subtract at the very end a minus 50. Okay? Having done this, we see that this term in the brackets is a geometric series with A equal to 100 and R equal to 3/4. And since our R in absolute value terms is less than 1, notice that I can that means that this means that our geometric series will converge, and the sum that it's going to converge to, we've already shown, has the form a over 1 minus r, which is a in this particular case is 100. This 100 is the first term, which is 50 times 2. 1 minus r is the 3/4. Okay? And so this is 100. 1 minus 3/4 is 1/4. So that 4 pops up on top and it multiplies the 100 to give us 400. But we're not quite done yet, because we said that the total distance has to be the geometric series part, which is what we just computed here, the 400, minus, of course, the original 50, which is this term. Okay? And so, if you account for that, the total distance that it's going to bounce is 350 meters. Okay, that's all we have for today's video. I hope that was instructive. We talked a lot about various terminologies, from sequences to the nth or the general term in a sequence. What is exactly a sequence? It's a ordered listing of objects. And then we went on and defined what we mean by an infinite series. Whenever you hear that word, think of sum. We talked about convergence or divergence of a series. We looked specifically to one particular type of a series. That's the geometric series that we were looking at, which is probably the most prominent of all the series that you will first encounter. And then, of course, in doing this, we developed some guidelines as to what makes a geometric series converge. Namely, what makes a geometric series converge is whether or not the absolute value of the common ratio r is less than 1. Like in this example, it was 3/4, which is in fact less than 1, because that's 0.75, which is less than 1. And so we know that that geometric series, which I have in these square brackets, is going to converge. It happens to converge in this case to 400, and we take out the fictitious contribution of the 50 that we added in, and that gives us a total bounce distance, or a total sum, if you will, of our bouncing infinite series, geometric series, of 350 meters. And I hope to see you in a future video once again.